Okay, we are going to pick up right where we left off. We're on page 225. So 225 in your workbooks. There are a couple mistakes in this activity. So this one here, this should be 4.5%. Okay, and then on page 227, we have one little issue. We need to have another lone pair on that oxygen. Okay. So this begins radical reactions, which you didn't really know it. We've already done some of, so they won't be totally new, but they're very useful reactions. In the first part, we see that fluorine gas up here, fluorine is not useful because it's too good at reacting and it's too fast and explosive, and it can end up with all sorts of products that aren't predictable. Chlorine, notice we have a fairly even mixture of products. We have this product distribution. So here we have a primary chloride, here we have a secondary, here we have a tertiary. Okay, so there are some differences there. With the bromides, less than 1% of the primary product, only 4.5% of the secondary product. Tertiary product wins by far at 91%. Okay, so describe the transformations in the reactions in Model 1. What is replaced by what? So at any of these, we can just take a look. So on the first chloride example, we have a CH3 here. Now we have a CH2 and a Cl. So the hydrogen is replaced with a chlorine. Let's look at one of the bromines. How about on the third one, we have a CH on that carbon. Here, that H is replaced with a bromine. So an H is replaced with Cl or Br. Which replacement of an H with a halogen, fluorine, chlorine, bromine, or iodine, is fastest and which is slowest? So fluorine up here, it says rapid and explosive. So this one, that's fast. If we follow that logic, we would think that iodine, which is further down in the halogens, would be slower. Okay, we see that in our next memorization task. Relative rates of halogenation. There's a huge difference between fluorine and chlorine, a big difference between bromine and iodine, but we see here in the middle that chlorine is just a little bit faster than bromine. Fluorination of alkane is dangerously fast. Iodination is so slow to be impractical. Only chlorination and bromination are commonly used in laboratories, and of those, bromine is even more commonly used. Each reaction in Model 1 gives a mixture of products. Based on the percentage of each product, what type of hydrogen is most likely to be replaced by bromine? Primary, secondary, or tertiary? So hit pause, figure out your answer, and then come back for the answer. Okay, you should have chosen tertiary. We see that here. It's most likely its percentage is higher. Because of symmetry, the starting material in Model 1, 2,5-dimethylhexane, has only one type of primary hydrogen, one type of secondary hydrogen, and one type of tertiary hydrogen. What is the ratio of the number of primary to secondary to tertiary hydrogens? So I'll get you started. Let's start by counting primary hydrogens. So here's our primary carbon, there's one, and there's one. So if we add up those hydrogens, we should get 12. So 12. So hit pause and find the rest of your quantities. Okay, we should have 4 secondaries and we should have 2 primaries. So we can simplify that to 6 to 2 to 1. Explain how the data in Model 1 support this statement. If there were an alkane with an equal number of primary and tertiary hydrogens, chlorine would be about 5 times more likely to replace a tertiary hydrogen than a primary hydrogen. Okay, hint, in 2,5-dimethylhexane, how many more primary hydrogens are available for reaction compared to tertiary? So again, hit pause. I'm going to give you some time to think this through. Okay, this is my explanation. There are 6 times more primary hydrogens than tertiary. Yet the number of primary chloride products is only slightly more than the number of tertiary chloride products. So we can kind of make a fraction out of this. So we have the ratio of tertiary to primary is 6 to 1. So this here, that's our ratio from up here, 6 to 1. That should be a primary though. Okay, so we want to know what this number is if we have one of these. So we can figure out that we have 20%, 26% divided by 32%, and that's going to give us 4.9, which is about 5. So to get that number, we're just going to cross multiply and divide, and then that's how we get to 4.9. Okay, so the answer is we would be about 5 times more likely to replace a tertiary. We see that right up here. That's what we were wanting to solve. Okay, if that didn't make sense, hit pause and play around with this until you can get this to make sense for you. Okay, going on. H-type or hydrogen type selection preferences for radical halogenation reactions are here. Radical halogenation reactions preferentially replace an H on an alkane according to the following order. First is benzylic, then allylic. So if you've forgotten what those things mean, go refresh your memory. Then tertiary, followed by secondary, followed by primary, followed by methyl. Okay, according to the data in Model 1, which halogen, chlorine or bromine, is more selective, more choosy when replacing an H on an alkane? Explain your reasoning. Okay, flip back to the data on the first page here, and how can we figure out which one of these is more fussy about which type of hydrogen reacts? And looking at this, remember chlorine 32, 42, 26. It's fairly evenly split. Here we know bromine does not like primary. It's really not that excited about secondary, but look what tertiary. Tertiary is 91%. So that tells us bromine is the more choosy of them. So the tertiary product far exceeds the secondary and the primary products. When compared to the chlorine reaction. Circle one answer that best fits the data in Model 1. Bromine is 2 times, 5 times, 10 times, 20 times, 100 times more likely to replace an individual tertiary hydrogen than a secondary. So, in other words, what's the difference between 4.5 and 91? And hopefully you're seeing that it is a 20 times 20-fold difference. Okay, are your answers to the previous 3 critical thinking questions consistent with the data in memorization task 15.3? And let's take a look. And we should say yes. Okay, so allylic, just a refresher. Allylic would be this carbon. Benzylic would be if we have a benzene ring. With a carbon chain coming off of it, the benzylic carbon would be that one. Okay, we have a couple more synthetic transformations. Chlorine gives a variety of products. Bromine is preferential for a tertiary carbon. So the bromine reaction is the one that we're going to use by far the most. It's going to be kind of one of the most common starting reactions because there are very few reactions where you can start with an alkane and do something with it. Alkanes generally don't like to react very much unless you can burn them, which isn't really that useful. You can do this with bromine and light, but NBS down here, N-bromosuccinimide is a common reagent for this. So this is something I want you to memorize. You need to know what NBS is. Okay, so make note of that. That's something that you need to commit to memory. It's a more useful reagent, maybe not more useful, it's more convenient than straight bromine. Straight bromine is nasty. It eats through lids of its bottles. It tears up or eats up the labels of its bottle and the ones around it. It's really reactive. NBS is a little more subdued than plain bromine. Model 2, polar and nonpolar bond breakage. Mechanisms in this course outside this chapter involve polar bond breakage, in which the 2 electrons comprising a bond move together as a pair when the bonds break, generating a positive and a negative charge. We've seen that several times, or we've seen that all last semester. Radicals, though, are species with an unpaired electron. Radicals result from the nonpolar bond breakage. So, for instance, down here we see bromine, that's a nonpolar bond. So a polar bond would be something more like what we see down here, right? The hydrogen and the oxygen have a big electronegativity difference. With bromine and bromine, there's no electronegativity difference. So again, remember down here we added those 2 electron pairs, so if you haven't done that, make sure you have that in there now, or you'll get confused. Okay, question 9. Add formal charges, if necessary, to the examples in Model 2. Okay, hit pause, add in your formal charges, and then come back and check your answer. Okay, bromine with 6 valence electrons, it needs 7 to be neutral, so if we have 6, we're going to be positive. If we have 8, we're going to be negative. Hydrogen wants 1 valence electron, so at 0, it's going to be positive. Again, bromine with 8, negative. And OH2, also known as H2O, that's water, it's neutral. On the right side, I don't think we have any formal charges. Wait, we missed one. Right over here, this is hydronium. Oxygen with 3 bonds, it has a positive formal charge. Okay, a double barb arrow. depicts the movement of a pair of electrons. Okay, we see that right up here. Double barb arrow, that's a pair of electrons. What do you think a single barb arrow depicts? We see single barbs right here. So in this case, we have a double barb over here, we end up with a lone pair. If we have single barb arrows, we end up with one electron on both Y and Z. So the single barb arrow, that's going to be movement of one electron, also known as a radical electron. Okay, circle all radical species in Model 2. I'll start. Here's one. Okay, hit pause and find the rest of them. Okay, all of these. These are all radical species because we have unpaired electrons. There, and there. Okay, that lone unpaired electron, that's what makes a radical. Moving on, we have a new memorization task about radical potential energies, and this is fairly important. Highest potential energy is a hydrogen radical, otherwise known as hydride, is very reactive. Going down to a halogen radical is the lowest in potential energy, therefore the lowest reactivity. This corresponds here with the reactivities that we saw earlier with the reaction rates at the top of page 226, so you can compare that if you want. Then you only have to memorize one thing. Radicals can be resonance stabilized, but they do not rearrange. Curved single barb arrows are used to generate resonance structures of an allylic or benzoic radical, which makes sense. Allylic and benzoic down here at the bottom end of radical potential energies are resonance stabilized. That means they're going to have a lower potential energy and be less reactive. In what ways are radicals similar to carbocations, and in what ways are they different? Okay, I want you to hit pause and I want you to think a bit. If you don't remember what a carbocation is, go look it up, but try to jog your memory. Okay, similar. Carbocations also lack an octet. Okay, carbocations, they can also be resonance stabilized. I don't think I can't come up with any other big similarities, but there's a big difference, and that difference is right here. Remember carbocation rearrangements? We have the hydride shift and the methyl shift. Radicals don't do that. So difference is they don't rearrange like carbocations. Model 3, Red Rover, send radical right over. If you grew up in the United States, you know what Red Rover is. If you didn't grow up in the United States, you may not know what Red Rover is. Radical reactions behave similarly to the schoolyard game Red Rover. However, unlike the kids' version of Red Rover, in the radical version, the radical bonds to one of the two atoms that it splits apart. Recall from oxidation reactions that a carbon-hydrogen bond is easier to break than a carbon-carbon bond. Okay, construct an explanation for why the bromine radical in Model 3 stuck to the hydrogen instead of the carbon. Hint, what radical would be produced if the bromine radical had stuck to the carbon instead? I'll give you a second to think about it. Hit pause. Okay, if it had done that, it would have produced a hydrogen radical, which, if you remember the table back here, right at the top of the screen now, is a higher potential energy. Remember, chemical reactions, they want to avoid high potential energy if they can. It's almost like they have a little mind telling them to avoid it. On 14, use curved single barb arrows to show the mechanism in the following step in a radical reaction. Okay, this one, we'll do this together because it's your first time. So using the curved arrows up here as an example, the bromine radical, this thing here, this is what comes in first, and this is what causes all the reaction. So it comes in with a single barbed arrow, like that. Now it's going to grab hold of this hydrogen, so we're going to bounce off like that. Okay, so what we've just done is this step here. This is something called initiation. This is where the reaction is going to start. Okay, so that bouncing arrow, this one right here, that moves one of the electrons to a new bond between hydrogen and bromine right here. So this electron and one of the electrons from here is now located in that bond. Okay, that means we have one electron left, and that's going to form a new radical right here. So the big difference, single barbed arrows with radical reactions, they're not going to move pairs of electrons like we've been used to so far. Construct an explanation for why the bromine radical in the previous question broke that particular carbon-hydrogen bond, even though there are 9 carbon-hydrogen bonds of the other type. In other words, this is the bond that broke. Why that one and not, say, this one, this one, this one? Why not any of those? So hit pause if you need some time to think, but the reason is it was the only tertiary carbon-hydrogen bond, the only tertiary carbon. So tertiary radicals, tertiary radical is more stable / has lower potential energy. That is why bromine chose it. Just like it has a little mind. We have a few sources of chlorine and bromine radicals. When elemental chlorine or bromine, that would usually be chlorine as a gas, kind of a greenish yellow gas, but it dissolves into liquid, like water. Bromine is an orangish brown liquid that gives off vapors very easily. So if either of those are exposed to intense light, a small number of chlorine or bromine radicals will be produced. Alternatively, exposing NBS to heat or light will generate bromine and radicals. Okay, use curved single barb arrows to show a multi-step mechanism for the following reaction. Okay, so this is going to take a little bit of thinking. So first thing we need to do is we need to make a radical. So we're going to have 4 reactions here, kind of spaced like this. So don't write this too big because we're going to have 4 big reactions in here. The first thing is we need to make some radicals. So we're going to do something like that. We saw this on the previous page. If you look on page 227, on the right-hand side, you'll see that happening. Okay, so that's going to give us bromine radicals. Okay, next we have our methane. And we're going to add one of these bromine radicals to it. So this step is going to be just like 14 on the previous page. So hit pause and figure out if you can do this on your own, and then come back and check yourself. Okay, unlike the previous page, we don't have any tertiary. We have one carbon, so we have one choice. So bromine is going to come over here and wreak havoc. I should draw that a little bit better. Let's try something like that. The other electron is going to end up on the carbon. Okay, so this is going to give us two products. We're going to have that radical. Notice there is no formal charge here. And we're going to have HBr. Okay, so now something can happen. We've used up one of these. Change the color of this. We've used up one of our bromines, but look here. Now we have a new radical reaction. So, for sake of argument, let's say that this new radical comes in here, and it encounters a bromine. What do you think is going to happen here? So it's going to be the same thing, that this radical is going to come in and say, hey, I need to react. Okay, so that's going to happen, or that could happen. So we're going to end up with our brominated product that we wanted. But look here, we have another bromine radical that we made. So that bromine radical, it wants to go tear apart another molecule and react with it. So another option that can happen, we see some hints of this down below. I might be getting ahead of myself a little bit, but we'll cover that if we get to it. What would happen if we have two bromine radicals, or two radicals period, come together? I guess I maybe should draw this a little bit differently. So how about here? If we'd have a bromine radical and those two radicals, then we can end up with another route to getting the product up here that we were after. Okay, so if those didn't make sense or anything, feel free to hit pause, rewind, give it another watch if you need to. A reaction between two radicals may seem very likely from an energy standpoint because, in such a reaction, two high potential energy species combine to form one low potential species. Right here, high energy, here, high energy, over here, low energy. Right? I told you before, chemistry loves to make low energy products. So that is a very, very downhill favorable reaction, but it's unlikely to happen. It's statistically unlikely to happen. Radicals are so high in energy that they react with anything that they bump into. This means a radical has a short lifespan and usually does not have time to find another radical. Radicals aren't terribly common, so by the time this bromine radical finds something else, most likely it's just another molecule. And it's so reactive, it doesn't care. It doesn't need another radical. It's just going to tear apart whatever it runs into. Picture the old Veterans Stadium in Philadelphia, which maybe you'll have to Google it in order to picture it, filled to capacity with 62,382 people. The Eagles fans are not normally peaceful folks, but on this day there are 5 violently reactive fans in the stadium that will start a fight with the first person they bump into, getting themselves thrown into the Veterans Stadium in-house jail. Assume the violent fans are dispersed randomly in the crowd. What are the chances that 2 of the 5 violently reactive fans get in a fight with one another? So, is that likely? Is it not likely? Hopefully you're starting to think that if there are 5 fans within 62,000 plus people, the chances are very low of 2 of those reactive fans running into another. Based on the information in Model 5, circle any step in your mechanism at the top of the page that has a low probability of occurring and explain your reasoning. So of these, which one is the least likely to happen? And hopefully you're looking at this one right here. Energetically it's favorable, but statistically it's unlikely. So that reaction, yes, it is favorable, but it is statistically unlikely to happen because they're 2 radicals. Okay, we're almost done. The first 2 steps of the mechanism from the previous page are drawn for you below. All right, we got those right. Methyl radical is like the fighter in the energy in the stadium and analogy. It will react with the first bond that it bumps into. What is the most prevalent species in the reaction mixture after step 2? Okay, after step 2, that means we're in this box here. What of these is most prevalent? And I hope you're looking at this little italic statement left over from the huge excess at the start. Right, bromine is in a huge excess. Show the statistically most likely step 3 in the mechanism above. Note, this step leads to the formation of a CH3Br, but there are also radical species left over at the end of step 3. So rather than drawing it, let's look back here. And let's label our steps. Let's call this 1, we'll call this 2A, 2B, and I think we'll call this one 3. So I labeled them that because step 1 is starting things off. Step 2A, those, we're going to give them a name here in a little bit. Those are both ones where a radical bumps into a non-radical species. The last one I labeled 3, not 2C, because that is 2 radicals coming together. So the statistically most likely step is going to be step 2B. Right, in step 2B, the new radical that we formed is going to bump into that really common Br2 that we have in excess of. I'm going to write on here previous page. Okay, so let's put some names to these parts. 3 parts of a domino chain reaction or a radical chain reaction. This is literally what you've heard chain reactions. So we initiate. It's kind of like playing with dominoes, where you start, you knock one over, and then it keeps tipping them down as they go on. So we have initiation, propagation, and termination. Initiation is the net generation of radicals. That's the first thing that happens. Propagation is where one radical is consumed, and when one's consumed, another one is produced. Termination is when radicals get used up and they don't produce any new ones. So at the top of the page, actually let's go back to the previous page, I think. Identify the initiation step, the propagation step, and a termination step on the previous page. Okay, so back here, hit pause if you need to, and we're going to label these. Okay, here we have initiation. We know it's initiation because a non-radical species forms two radicals. This is a propagation. We call it propagation 1, and this one is also a propagation. I'm just going to call it propagation 2. We know it's propagation because a radical comes in, forms a new compound, but it also produces a radical. Same here, a radical comes in and ends up producing a new radical. So that's called propagation. Propagation is a word that means to produce. So, for instance, if you were a botanist, you are propagating plants, you would maybe go to, say, a tomato plant, take cuttings from it, and then you would take each of those cuttings and you would start a new plant from those cuttings. Okay, the last step, this is going to be the termination. Termination because two radicals come together and they terminate the reaction, or that particular radical is terminated. A collision between two radicals is unlikely, but it does happen every once in a while. Eventually, such reactions will stop the chain reaction. List at least two possible chain terminations. They don't all have to end up as being bromomethane. Okay, I want you to hit pause here, and I want you to give me three possible, well, they say two possible. I think you can do three possible termination steps. I'll give you the first one. Bromine radical plus bromine radical is going to give that. Okay, now hit pause and come up with the other two. Okay, we have another two radicals, so this one can give us this product. We could also have these two radicals. I'll write it like otherwise known as ethane. So there are three possible termination steps. All of them unlikely, but possible. Okay, that's where we're going to end. Check Moodle for your homework assignment / quiz that I want you to work on and upload on as a photo onto Moodle. And make sure you have all your other work done. Aside from that, we're going to call this good for the day. All right, have a good day.